Alright, today we're going to look at conservation of energy. Last time we talked about work and power and potential and kinetic energies. Today we're going to look at systems where we start with one type of energy and then it's transferred into another type of energy. So we have a few new equations today. The first one is right here. The total energy initial is equal to the total energy final. So again, we're assuming that we are not going to get any energy loss. And the total energy is made up of the kinetic and the potential. Again, we're dealing with mechanical systems, so we're not going to take into account friction, heat loss, those kind of things with our system. So it's just kinetic and potential. And from yesterday we learned that potential energy is just mgh, so this is gravitational potential. It's based on the height, mass, and the gravitational acceleration. And then the kinetic energy is 1/2 mv squared. So those are the equations that we're going to be using today to solve. So let's look at our first problem here. We have two problems that we're going to look at today. We're going to break this down into steps, and then for the second problem, basically I'm going to show you how to substitute and solve instead of doing each of these individually. We have a 500 kilogram rock. It's pushed off of a cliff that's 200 meters tall. So I've drawn a picture over here off to the side. I'd encourage you to do that on all of these problems from here on out. It just makes it a little bit easier to visualize what's going on. At the top, we just have a rock and it's pushed off, so it starts to accelerate as it falls down and hits the ground. Now let's just kind of initially figure out what's going on. What kind of energy does it have sitting up here at the top if it's moving with a velocity of 0? Well, we could say that it has an initial potential, and the initial kinetic energy is going to be 0 joules here at the top. And then when it strikes the ground, the moment that it strikes the ground, it has a kinetic energy down here, and now the potential energy is 0 joules. So our energy has transferred from potential energy to kinetic energy. And we're going to see that worked out in this problem. And again, the reason why kinetic energy is 0 here is because the initial velocity is 0. And the reason why the potential energy is 0 down here is because its height is 0. But again, that's going to be shown through this. So let's look at part A. It says determine the potential energy of the rock at the top. So we want to find its initial potential. So we'll put PE initial is mgh. And we're just going to substitute. Mass is 500 kilograms, G is 9.80 meters per second squared, and the height is 200 meters. And we can do all this in our calculator. So we have 500 times 9.8 times 200, and we get this value. I'm going to put it into scientific notation. And again, if you are unfamiliar with that, we're just moving the decimal place so that we have it's to the right of the first non-zero digit, or we can use the SCI key in our calculator and it'll do it for us. So that's how much kinetic or potential energy we have at the top. We talked about this. How much kinetic energy does it have while resting at the top? Well, that would be 0 joules. It's not moving. So what's the total energy of the rock at the top of the cliff? So total energy is potential plus kinetic. We could substitute our values. I'm a big fan of arrows. So this comes out to be 9.80 times 10 to the 5th. And again, if this number was not so nice and this number right here wasn't 0, I'd make sure that I carry extra digits and underline them for these to show my addition rule in my answer. At the bottom of the cliff, what will the potential energy be? Well, we've talked about it. It's going to be 0 joules. And now at the bottom, all of that energy that we had to begin with has been converted to kinetic energy. So our kinetic energy at the bottom, if we find that, our KE final is equal to the total energy minus the potential energy. And we got that by rearranging this equation right here. And we know that the final total energy is equal to the initial total energy. So if this is our total energy initially at the top, then that's our total energy final at the bottom. and our potential energy final is 0. So basically our kinetic energy final equals our total energy final, which equals our total energy initial. So we get a value of 9.80 times 10 to the 5th. It's the same number. Now we want to know what's the velocity of the rock at the bottom. So we're using this equation up here, solving for velocity. So if I use some algebra, I'm going to multiply both sides by 2, divide both sides by m, and then take the square root. So I get this equation here. I'm going to substitute 2 times 9.80, going to carry an extra digit there. Mass is still 500 kilograms. I can do this all on my calculator. So I've got 2 times 9.8 E5 divided by 500. Make sure you take the square root, and I get a value of 62.6. Again, good to 3 digits, 3 digits, answer's good to 3 digits. Units are going to be meters per second. Now, F's a little trickier. What will be the values of the kinetic and potential energy of the rock when it's falling at a speed of 20 meters per second? So when it hits the ground, it's going at 62.6. So when it's going at 20, we're not to the ground yet. We're somewhere in this region. So it's fallen a little bit, but it's not fallen all the way. So we have a potential, and we also have a kinetic. So what can we solve for using this speed? We can solve for the kinetic energy at that point. So that's going to be 1/2 500 times 20 meters per second quantity squared. So the kinetic energy at this point, if I plug it in, 0.5 times 500 times 20 squared is this value. Now, think about what is constant. What is constant here, 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 anywhere along this path? What is always true? Well, the total energies are always equal to each other. So the total energy here is the same as the total energy here, which is the same as the total energy here. And that total energy is how much? Well, if we look back over here, it's 9.8 times 10 to the 5th joules. So if I say the total energy is equal to the kinetic energy plus the potential energy, can I solve for the potential energy now? Sure. So the total minus the kinetic. So I have 9.80 times 10 to the 5th joules minus 1.0 times 10 to the 5th. So the potential energy at this point is going to be 8.8 times 10 to the 5th joules. I like to box in my answers. It kind of highlights them. Makes it look good. So hopefully that makes sense to there. I'm going to let you try to do number 2 on your own, part A, so pause the video. Okay, here's the solution that I came up with. I got a value of 195 meters for the height that it's at currently. Let me step you through how I got there. I used the substitution method. I'm going to show you the other method here in just a minute if you don't want to do this. I had initial and final total energies are equal to each other. The total energies are potential plus kinetic, so I have that on both sides. And I did a little substitution here where mgh is potential and 1/2 mv squared is kinetic. Now if you notice, I canceled out the initial kinetic energy. That's because the rock is sitting at the top of the hill here initially, so it has 0 kinetic energy, so I can cross that right off of there. You'll also notice that the masses are canceled. Well, because each of these terms has mass in it, if I divide everything by m, all of these values cancel out. And just like we know that when things fall and are dropped, they do not depend on their mass, on how they move. So we see that here as well. And then I'm solving for the final height of the rock. So I do some algebra here. I move the 1/2 v squared to the other side, so it becomes a negative. And then I divide both sides by g, so when I have g times initial height, divided by g, I get initial height. Subtract off 1/2 v squared divided by g. So this is my final equation to find the height. I substitute in my values. I solve for this little section here to show my subtraction rule. And again, I'm good to the ones digit, good to the hundredths, so my answer is only good to the ones digit when I subtract. Now let me show you a different way to do this. I've got this typed out here. But you could have solved each of the spots along the route. So in this case, I could have found the initial potential energy and found the final kinetic energy using the velocity there. Here I'm using the initial height. And then from that, I could solve for the final potential energy by this equation right here. So I found the initial potential, the final kinetic, and then I'm going to solve for the final potential, which is right here. And that value then is equal to mgh. So to find the height, I then divide both sides by mg. Plug in those values and get a height here. So you could do this work where you're solving individual components of this instead of doing the substitution method, which is then shown here. So again, there's a couple ways to do it. Again, I'm going to let you try part B on your own. Pause the video and then come back and see how you did on part B. Okay, so let's say you tried it, you're looking at it, and you can see that I haven't solved anything because I want to make sure that you have the setup correct. So again, we're still on this cliff, but now we're throwing it downward. So now it has a kinetic energy here and a potential energy up here. Kinetic energy is no longer 0 at the top. And then we want to know at 100 meters above the ground, what is its velocity? So here it also has potential and kinetic energy. So hopefully that'll get you started. Pause the video again, see if you can do it on your own, and then come back. Okay, so here's the final answer. You do get 45.4 meters per second in both cases. So I've shown the work for both methods here. This way is typically easier for students starting out. You can find your initial potential energy based on the height. You can find your initial kinetic energy based on its initial velocity. From those two, you know its total energy, and you also know the final potential energy is this value here because now it's at 100 meters. So from those three values, using this equation here, you can solve for the final kinetic energy. And once you know the final kinetic energy, you then can find the velocity. Remember, if we're using algebra here, velocity is going to be 2ke divided by m, and then you're taking it to the square, you're doing a square root, so it's the 1/2 power here. And then I plug it in. Here's my final kinetic energy, here's my mass, take the square root, here's my final velocity that I get. This is the method that I would recommend for most of you. It just is a little bit easier if you solve the individual parts. If you love substitution, you could get it to this point here. Again, your masses cancel at this point. Then we want to multiply everything by 2 to get rid of this 1/2. And then we want to take the square root. So that's what's been done here. You can then substitute your values in. Again, showing your addition rule with keeping your extra digits here as you go through, and then finally taking your square root at the end. Again, you have a lot more to worry about in terms of units and getting your units correct. But typically it's less work than doing, multiple steps here. So either way, you can do the same thing. And kind of the neat thing here is if you look, you'll see that this equation, we've seen it before. This looks familiar, right? So if I solve for VF, it's equal to 2AD minus V initial squared, and then I'm taking the square root. Everybody okay with that? That would be a plus. So if I look up here, how is that the same? Well, what is the distance? The distance is the difference in height. Did everybody see that? Distance in height, or difference in height? So this equation is actually the same as this. You could use kinematics equations to solve. We're using energy equations this time to solve for these problems. Hope you enjoy.